So welcome to Math 383 Complex Analysis. This is lecture 21. So what we're going to do today is we're going to continue talking about conformal maps. We will hopefully get to things like the Schwartz lemma, talk a little bit about automorphisms of the unit disk. A lot of this is going to be very similar to the change of base formula from the theory of logarithms. We want to convert things to just one item that we need to understand. It's the same thing in statistics. We convert to the standard normal. This way we don't need tables or things for all these other distributions. We just need it for one. So for many things, it turns out, and this is the beautiful Riemann mapping theorem, whatever you want to study, if it's reasonably nice, turns out to be conformally equivalent to the unit disk. And then there's a huge subject, what is conformally equivalent to the unit disk? Which things can I look at? We've talked about which contours we integrate over. For the most part, what contours do we consider in this class? Simple, right? Give me some examples. Semicircles, rectangles, pizza slices, or something with finitely many, places that blows up. We come in, zoom around, and come out, which then just gives us a bunch of circles. You can prove results for more general contours if you need to really, really integrate, and then you use some topology. But for the most part, those simple regions are more than enough for everything we need to look at. So similarly over here, there's a couple of key regions that are conformally equivalent to the unit disk. And we'll talk a little bit about some of the mappings, and we will discuss the proof of the Riemann mapping theorem, which shows you just how far can you go. Okay. We talked a little bit last time, just very, very quickly. The beautiful proposition, which is very different, not surprisingly, than real analysis, is if I have a holomorphic injective function from U to V, then the first derivative can't be zero anywhere in that set. This is extremely different than real analysis. So the example you all should have seen is the function f of x is x cubed, right? This is one of the functions that makes calculus hard. Because if I want to try to find where's this function maximized, where's it minimized, I look for the critical points. Where does the first derivative vanish? So if I take the derivative of f of x is x cubed, I get 3x squared, that vanishes at the origin. So you would expect, oh, okay, it has a critical point at the origin. Let's check to see, is it a maximum or minimum? You then take the second derivative, and you see that the second derivative is zero, which means the second derivative test fails. You can keep taking derivatives, and you can do the third derivative test. You can also do the first derivative test. If you don't remember what those phrases are, look them up. If you can't find them, ask me. But you should know what the first derivative test is. You should know what the second derivative test is. You can also just plot the damn thing, right? And if you plot x cubed, you can see this function is clearly increasing throughout the entire region. The first derivative is zero. And so the slope becomes quite interesting as we get near the origin. Now, if you try to find the inverse function, which is a fun game, so we say, g of x is going to be such that f of g of x is x, you get g of x cubed is x, so g of x is x to the 1/3, which is not differentiable. So things can break down tremendously in real analysis. Here's a situation where my first derivative can vanish, but it's an injection. It's actually a bijection. Unfortunately, not only does the first derivative happen to equal zero, but the inverse function is not even differentiable at that point. So I want to talk today a little bit about why, again, is real analysis so different than complex analysis. All right. I went in the wrong direction. Okay, here we go. So I'm not going to go through the details. This is one of the proofs in the book. There was one thing that just bothered me, and so I went a little nuts, I think, with the red ink. Who knows what the WLOG stands for? Without loss of generality. So when you're doing problems like this, make your life as simple as possible. Without loss of generality, if you're looking at a point that's special, what is that special point? Zero. And without loss of generality, what's the value of the function at zero? Zero. Typically, we can do this to just make things a little bit easier. Let's just translate and set the key point to zero. Let's rescale. This is typically not a big deal. And so I'll talk a little bit about this in a moment, but what's really going on for the proof that the first derivative is not zero is Rouché's theorem in the background. All right. So we've talked a little bit about, just I mentioned a moment ago, adjusting that without loss of generality. I can choose a very nice function that's going to translate. And I can just shift z by looking at maybe z minus z naught. And then I can subtract off a constant. I can subtract off f of z naught. So it's not a big deal to adjust things. You don't have to do that. I just like to do it to keep things a little bit simpler. All right, so let's talk about why real and complex are so different. So here's the function f of x is x cubed. Here's the function f of z is z cubed. Do we agree that both of these basically take, here takes -1, 1 to -1, 1. It's 1 to 1 and it's onto. But what goes on here? It does take the unit disk to the unit disk. Is it 1 to 1? No. Is it onto? Is everything hit? Yes. For the most part, other than one point, how badly is it not 1 to 1? Pretty bad. Quantified, how much? Yeah, it's really 3 to 1, say for the origin. And if you go back to multivariable calculus, if you go back to your spherical coordinates and your polar coordinates, these transformations break down at the origin. There's not a unique r and theta for 0, 0 down there, but it's breaking down at just one point that doesn't really affect the integration that much. It's often glossed over. So this is essentially a 3 to 1 map, except at the origin where it's a 1 to 1 map. Okay, everything is hit. If I want to visualize what's going on, again, my artwork is horrible, but with a reasonable imagination, this is a unit circle. Okay, if I take my unit circle and I look at the first third of the unit circle, okay, so this would be, z is r e to the I theta, 0 less than equal to r less than 1, 0 less than equal to theta less than 2 pi over 3. Or less than equal to, I don't really care. And what happens when I apply my cubing function to this green region? What happens? It covers the whole thing. So this covers the whole thing. And then the next third of the circle extends and covers the whole thing. And the next extends and covers the whole thing. So when I try to look at the function, z goes to z cubed, it covers everything 3 times except for the origin. What's going on when I look at -1, 1? So here, here's -1, here's 0, here's 1. If I apply the cubing function, where does 0, 1 go when we cube it? It goes to itself. And I'll use a different color. Where does 0, -1 go to? It goes to itself. Let's try to imagine what's going on. How could you write a number between -1 and 0? To mirror what we did with complex, I could write these as r e to the I theta, 0 less than equal to r less than equal to 1. And then what would be my angle? I'm sorry? Nope. Pi. Theta equals pi. Right? I'm on the negative real axis. There's only one angle. So now, if I send z to z cubed, r e to the I theta goes to r cubed e to the I 3 theta, as theta equals pi, e to the I 3 theta equals e to the I theta equals -1. Yes?
Why can't theta be like 0?
I'm in the red zone.
Oh, you're only.
I made it into the red zone. Right? I'm only looking from 0 to -1. I'm trying to explain why is this so different in real than complex. In complex, z goes to z cubed, triple covers things. Why is it not triple covering things here? Well, what's really happening is this is going around all the way and coming back to itself. Right? I start off at pi and I go all the way and I come back. So I go from an angle of pi to an angle of 3 pi. Whenever possible, you want to get a sense of why is real analysis behaving differently than complex analysis? Because I'm only looking at two separated parts, each part is just going back to itself. When I look at the disk, this whole region, the first third of the circle, expands out and covers everything. And then the next third will cover everything again, and then the next third will cover everything again. Okay? So this is high level what's going on. With a little bit more detail, imagine f of z equaled an z to the n plus dot dot dot. Okay? And I claim we have issues if n is greater than or equal to 2. It won't be injective. And here's the proof sketch. If we had, an z to the n, clearly it's not injective if n is greater than or equal to 2. Does everyone agree that if n is at least 2, if I just give you the pure polynomial an z to the n, it's going to cover things n times? And then what you do is you argue, if I give you a more general function, if z is sufficiently close to 0, everything else is negligible. And you essentially have the function an z to the n. How many zeros does an z to the n have? N. And so if I then have a slight distance away from it, everything else is going to be so small, I can use Rouché's theorem and get that I'm still going to have n zeros. So now just now add in an plus 1, zn plus 1 plus dot dot dot, very small if the absolute value of z is small, use Rouchet. So that's the high level explanation of what's going on. It's a Rouchet argument again, that if I have a pure function z to the n, I can understand that. Without loss of generality, what can I assume for an? 1, right? I'm just multiplying everything by a fixed number. Okay, I really don't have to worry about multiplying by a fixed constant. I could make an equals 1 if I wanted to just simplify the notation a little bit. I essentially just have z to the n, that's not injective. And then you can just go from that to, if I don't have a pure z to the n, if I have other stuff after that, that other stuff becomes so small if z is very close that I can use Rouché's theorem to say that they're close, and therefore they must have the same number of zeros. How does, yes?
Yeah. Should I be adding a minus 1 into this? Why is it a plus 1?
No, because I'm adding the next terms. If instead of having just an z to the n, if I had more terms.
Oh, I thought the terms are, oh, never mind.
Right, right. So I'm assuming, if I just have the function an z to the n, I know this can't be injective. And so if I have an z to the n plus an plus 1 zn plus 1 plus dot dot dot, if I have more and more terms, all those other terms are eventually going to be negligible. We write the function as an z to the n plus something really, really small. And then you just use Rouché's theorem. Yes.
So will our goal be like to approximate our function into some sort of like exponential that will like never terminate?
No, not an exponential. It's just use Rouché's theorem. We know the function z to the n or an z to the n has n zeros. If I look at this other thing, very, very close to z equals 0, it's going to look almost exactly like an z to the n. And then by Rouché's theorem, they have to have the same number of zeros.
Oh, so we're trying to show that.
So this would violate injectivity. So if we're assuming that the function is injective and that the first derivative vanishes, we get a contradiction. So what I'm assuming here is I'm assuming n is at least 2 because we're assuming that the first derivative is not 0. If the first derivative, we're assuming the first derivative is 0. So because the first derivative is 0, n is at least 2. If n is not at least 2, if n is 1, now that doesn't, we're not proving that any function whose first derivative is non-zero is injective, right? We're just saying that if you want to be injective, your first derivative has to be non-zero. Because if your first derivative is not 0, then in the small neighborhood, I can show that it's not injective. So we now know it is necessary that the first derivative is not 0. We do not know that it's sufficient, but we know it's necessary. In a very small locality, it should be sufficient to be injective. But maybe if you go sufficiently far away, it's going to break down. So this gives us a proof that if I have an injective function, the first derivative has to be non-zero, because if the first derivative was 0, then in the Taylor series expansion, which I know exists because it's holomorphic, the first term would have to be at least a z squared. And if it was exactly z squared, we know it's not going to be injective. If it has other terms as well, the pollution is so small that it's not going to really matter in the limit. So this proves that the first derivative has to be non-zero if you have a complex injective function. Very different than the real analysis case. Now, if you have something that's 0, what do you have to be very careful about? When you divide, you can't divide by 0. So this tells us I can actually divide by f prime if I'm working with a holomorphic injective function, and I don't have to worry about f prime being 0. If I'm looking at a real injective function, I could have f prime be 0, and that's where the problem comes from. Okay. So moving on, I'm not going to go through the rest of the details of the proof, but you should notice over here, oh, we are seeing an f prime coming in the denominator of something. And that's not surprising now after what we've discussed, that we can handle something like that. In the proof that they were doing, I might have mentioned this very briefly, they want to assume that we have something that's non-zero. Well, if f prime is not 0, then we know, by the accumulation theorem, we can't have infinitely many points close to it that are 0. So if we know f prime is not 0 at 0, there has to be a neighborhood about it where it's never 0. Otherwise, there would be infinitely many points getting closer and closer and closer, and then they would accumulate, and we know that f prime is not 0 at 0, so we can't have points accumulating. So, yet again, the accumulation theorem comes to our rescue. And this should give you a sense of why complex analysis is again going to be giving very different results in real analysis. We don't have anything like the accumulation theorem in real analysis. Yes? So we're assuming f prime is. Oh, we're assuming is okay. We're so let me see. Right. Oh, so okay. There's two ways that we could be looking at this. One way is if it's 0 at 0, it can't be 0 nearby. Because if it was 0 nearby, then it would be identically 0. Or you could say if it's not 0, it has to be not 0 in a neighborhood. And that would actually just be by continuity. Yes.
Are there a lot of functions that are holomorphic and injective? Because like that's like, and it seems to be like very rare to obtain such a function.
Well, I mean, for a lot of things, you need the first derivative to be 0 to have a chance of not being injective locally.
So we were just looking at the local.
Just local.
Not
right. But again, if I give you functions, it wouldn't be surprising that there are multiple values that are sent to the same output. But locally, we might expect that if we zoom in sufficiently close, that at most points things are injective. So as long as the first derivative is not 0, then we might expect that locally maybe everything will work out. Okay, I'm not going to go through all of this. What I strongly encourage you to do is just take a piece of paper and play with things, or if you want, program your computer to play with things. So here are two maps, F and G, and the claim is that the map F takes H, which is the upper half plane, so it's all points x plus I, y, where y is greater than 0, and maps it to D, which is the unit disk, all z, which are less than 1 in absolute value. It is sometimes hard to visualize what's going on. The best thing you can do is try to play with this, or somehow learn how to think four-dimensionally and look at a complex plot of a complex function. Not happening. You can sometimes play games and you can plot the absolute value of your complex function, but you're going to miss out a lot. So what I did here is I did parametric plots of the function f. So f of z, I'm writing it as the real part of f of z and the imaginary part of f of z. Okay. And so I can define my function, everything is nice, and I'm going to plot f of t. T goes from minus c to c. C is going from 0.01 to 10. And so when you look at this, that's going to be the first one. It's centered at the origin. The next one, it's t plus 0.5i. It seems like the center has moved a little bit. Let's look at the first one. Let's look at f of z, and let's plot it at t, where t goes from minus c to c. So t is a real number. So f of t is going to be I minus t over I plus t. How would you try to understand this? So go back to your algebra days. D-A-Y-S, not D-A-Z-E. Yes, what's that called? Yeah, take the complex conjugate. So we have an I minus t, I minus t. You might have heard the phrase, rationalize the denominator or something like that. And now if we do that, we're going to get that this is going to be, the denominator is going to be one, I'm sorry. The order I wrote things in was not the order I want. So I should probably do it like this, right? And so now the denominator is going to be t squared plus 1. Yes. And the top, I'm going to get t squared. Oh no, negative t squared, right? And then the minus I times I is 1. And then we're going to get minus IT. No, so we get plus IT and plus IT. So it's going to be plus 2IT. So it should be, goes to 1 minus t squared over 1 plus t squared. And then 2IT over t squared plus 1. If you look at this, I claim that this is going to be a point on the unit circle. Oh, I'm sorry, this shouldn't be an I div anymore because I'm writing it like this. How can you check to see if this is a point on the unit circle? Yeah. Yeah, take the magnitude squared. You'll get 1 minus t squared plus 2t squared over 1 plus t squared squared. You'll get 1 squared t to the 4th minus 2t to the 4th, minus 2t squared. You'll have a plus 4t squared that's going to. So if you do the algebra, you will see that this lives on the unit circle. And so when I plot it, I'm getting the unit circle. So I know my x coordinate is always going to be between minus 1 and 1. I know my y coordinate is always going to be between minus 1 and 1. And I know the sum of the squares is going to have distance 1 from the origin. Now I'm only plotting it from C. So my input is going from 0.01 to 10. And if you look, I'm not getting the entire unit circle. So how do we get to the point -1? What's going to correspond to -1? Was there any value of t that would correspond to -1? T is real. Which infinity? Negative infinity? Does it matter if I go to negative infinity or positive infinity? No, as t gets really, really large, I'm going to get negative t squared over t squared. The 1 is insignificant. So as t is going off to positive infinity, this is going to be going to -1. What do I get as t goes towards 0? Yeah, you get the 0.1. And so t is going to plus infinity, minus infinity. So it's good to just be able to play some games and get a sense of what does the function look like, what does it do. The best way to gain a sense is to just play with these maps and write them down. Most of you are not going to become professional conformal mappers. Oh, one of you might. Okay. Oh, okay. Oh, you just got to. I was so excited that I finally had a student. Yes, Professor Miller, I want to be a professional conformal mapper. Right. So the question is, how valuable is it to know this? It's important to know that stuff like this exists. This is the 21st century. Is it worthwhile to have these memorized? No. If you work in this subject, you will eventually learn certain maps and you will know them backwards and forwards. But this is like tables of integrals. You can just look them up. All right, so here's some other ones that you can play with. And so I've got the Mathematica code here that you can just grab and play with. Here is a nice map. F of z is 1 minus z over, I minus z over I plus z. That's exactly what we had a moment ago, right? And this is just going through the algebra and saying, let's say I give you some w in the unit disk. Can I find a z that's sent to that w? And this is just going through the algebra steps and trying to solve. And we get z, after you do some algebra, is I minus wi over 1 plus w. So we have found a z that's sent to w. The only thing we have to be careful about is we've said that f maps the upper half plane to the unit disk. So you have to show, is this in the upper half plane for given w? How would you show that this is in the upper half plane?
Given a w.
Given a w. So I give you a w in the unit disk. So w has absolute value less than 1. How would I show that this lives in the upper half plane?
The imaginary part of that is 1 minus w over 1 plus w and 1 minus w.
Good. So calculate the imaginary part and show that it's positive. Show imaginary part is positive. And if you can do that, then you know it does have z in the upper half plane being sent to w. And what's nice is this will show you that, in fact, that there's only one z that can work, because when I do all this, the algebra forces a z on me. So this is basically at the level of, I think, algebra 2, right? It's really nice that so often in complex analysis, we reduce these hard problems to, I need the negative first coefficient. I need to just do some algebra games. I need to just invert my map. So we really can avoid a lot of, the integration theory that you've spent, 3 semesters learning. All right. Fractional linear transformations, also been called Mobius transformation. I give you a matrix, say gamma equals A, B, C, D, and I give you some complex number z, we define gamma of z to be AZ plus B over CZ plus D. Am I allowed to do this?
Wasn't there a condition like A times B times C plus 1?
That might just be restricting which matrices I look at. Right now, I want to be, completely free. Well, I'm giving you a rule. You give me a z, and I'm going to look at AZ plus B over CZ plus D. Yes. Okay. So I will accept that as a friendly amendment. So will you allow me to do this if z does not equal negative d over c? Am I allowed to do this? But use the word define. Right? I can look at whatever the hell I want, as long as it's well defined. There was, I'm sorry?
As long as C is not 0.
C could be 0, or if C and D are 0, right? And let's say C and D are not both 0. I'll accept that as another friendly amendment. And then if I had accepted the friendly amendment that I shot down earlier, that should I put on some conditions on AD minus BC, then your complaint would not be valid, because by accepting that, I would ensure that C and D are not both 0. But I have to agree to at least one of you. I can't pass on both of you. So I can define this. The question is, when is this useful? What kind of properties does this have? This is a way to have matrices act on numbers. As soon as you have a matrix act on a number, what could you do to the output? You could do the inverse, and you could say, okay, if I know that the output is W, what Z gives me W? But what else could I do? If I apply the matrix to my number and I get something, what could I do next? Well, that was just said, yeah. So I took one matrix and I applied it. I could apply again, I could apply another matrix. So what if I had, gamma K is, AK, BK, CK, DK. So I can calculate the matrix, gamma 1, gamma 2, acting on Z. I can calculate gamma 1 on gamma 2 of Z, right? I could calculate gamma 2, gamma 1 of Z, and I could calculate gamma 1, gamma 2 acting on Z. I can compute all of these things. Yes?
I think I've seen somewhere something like this, and it requires ED minus BC plus minus 5.
Nope. I can just do these calculations. Now, when I write gamma 1, gamma 2, I mean, take the matrix by multiplying gamma 1 and gamma 2, and then apply that to Z. The gamma 1 acting on gamma 2 of Z is first take the matrix corresponding to gamma 2, apply that to Z, take that as your input, and now use the matrix gamma 1. What do you hope would be true? We hope that they would be equal, right? Conversely, if we start in the other direction, we hope that they would be equal. What about the middle? Gamma 1 acting on gamma 2 of Z and gamma 2 acting on gamma 1 of Z? Probably not. Why not? Yeah, matrix multiplication is not commutative. So I would be shocked if that works. Yes?
Isn't this how to say, this transformation basically just multiplying this like this matrix with the vector Z1, and then
you can absolutely view it as A, B, C, D on Z is like A, B, C, D on Z1 would then give you AZ plus B, CZ plus D. And then we associate that back to the number AZ plus B over CZ plus D. And really, Z1 we're associating to Z divided by 1. So if you want to try to look projectively or something like that, there are ways to interpret it along these lines. Do you think this is going to be difficult or hard to prove the reds hold? How would you do it? What do you mean by write it out?
Like A1, B1, C1.
No. I mean, are you talking about you physically writing it out? Okay. How else could you do it? I mean, you have to then show that it's consistent at the end. So you should.
Doesn't this argument make it? Because once you write it in matrix form.
Basically, I mean, what I would do is I would just sort of listen to Mathematica and have it spit everything out, right? I'm not going to multiply matrices, but anyway, learn to use these things as a tool. I am debating giving you an exam to grade. I had a former student who has access to ChatGTP and premium ChatGTP try to do the complex analysis midterm. So if you want, as a homework problem, you can grade ChatGTP and see, how well did it do? And where do you think ChatGTP is just bullshitting? And is it just like throwing in some words to make it look like? So, again, this is the 21st century. I've been talking with people about, how slow we are to change. It's wonderful. I mean, I don't use them, but we're surrounded by blackboards. We would be upset as a department if we did not have blackboards. This is the 21st century. What should you be doing? You should be learning as a go-to default to have these computer programs doing a lot of the painful, tedious calculations for you. And a lot of it is trying to figure out how to write things in such a way that you can investigate many cases quickly. And so as soon as I start defining things like this, I can start plotting things, I can visualize things a lot better. I really want you to be getting into that mindset. Okay, here are a bunch of standard transformations we should look at and know. So the first is f of z goes to z to the alpha. What do you think you can tell me about that alpha? When you look at this, it's taking the upper half plane and mapping it to a pizza slice. What do you think is true about that alpha? Less than one, because it's compressing it. I think you could even do better than, looking at this picture, it's less than 1/2. Maybe it's around 1/3. I don't know, but it's definitely less than 1/2 just by looking at this. The next one is, here's a map from the semicircle to the quarter plane. Then we have a map from the upper half plane to a strip. More maps. We have a map from the semicircle to a half infinite rectangle. We have a map from another half-inch vertical rectangle to a semicircle on the right, to a semicircle on the left, to, you can basically compose lots of these maps. Does anybody know about the postal metric? So if I want to measure the distance from myself to a place, we normally do the Euclidean distance, right? How does the postal metric work? Anybody ever see this in your analysis?
It's the British Railway metric that they taught us.
Okay, could be. What's the British Railway?
You go to London.
Yes,
you want to go.
exactly. So the way it works is you first send your letter to postal headquarters, and then postal headquarters sends it wherever you want to go. And so once you have these maps, if I can map anything to the unit disk, I first map something to the unit disk, and then I map it from the unit disk to what you want. So when I'm looking at all these different things, if I have a map that takes everything to the unit disk or everything to a standard fixed shape, I can then get from any shape to any other shape by just iterating. So first go to the unit disk, and then go from the unit disk to where you want. So my father worked in high tech for many years, and basically it was annoying because every company had their own language. And so if you wanted to talk to another company and you wanted the computers to interface, it would often be difficult because they would have their own language. But there was one computer company that had a huge market dominance. Anybody know what this was? This was decades ago. IBM. Everybody had to speak IBM. And so if necessary, you would just start speaking in IBM and the other company would speak in IBM back to you, even though IBM wasn't involved. It was the common language that everyone could use. It's the same thing here. If I have all these different maps, I can then combine these maps in various ways. So I just need to know how to get to one shape, if I can then invert my maps. Okay. And so I think we already talked about this one. Or I think I went backwards a little bit too much. Okay. So here, some more fun maps, just playing with things. This is an extremely important function. C alpha is defined as alpha minus z over 1 minus alpha bar z. So alpha is a complex number less than 1. And I've set up some code so you can actually play with this and see what it does. Are there any inputs where you can tell me what C alpha will send you to? There should be at least one input where you can look at this and you know where it's going to go. Okay, where does 0 go to? Goes to alpha. And there's one other one that you should be able to look at very quickly. Yes, alpha. And where does alpha go to? To 0. So this map switches alpha and 0. Other than that, it's a little bit hard. Now, what would C alpha of 0 be?
Is it product or composition?
Composition. So I'll do it this way. So that would be 0. And similarly, what would C alpha of alpha be? Alpha. Therefore, C alpha is its own inverse. Right? I showed it for 2. Have we done this in class yet, 16/64? Okay, if you've seen this in a previous class, you're mute. Have we done that in this class? In lowest terms, what's 16/64? Quarter, that's taking you way too long, guys. 19/95. 19/95 is 1/5, 49/98. Come on, this is taking too long. 1/2, 12/24, 1/4. And as was remarked, you cancel the 6s and you get 1/4. You cancel the 9s, you get 1/5. You cancel the 9s, you get 4/8, which reduces to 1/2. So clearly, if I cancel the 2s, I get 1/4. Just because something holds for a little bit does not mean it will always hold. Some of you might have seen the Euler polynomial that only takes on prime values for the first 40 or so inputs. Patterns can hold for a while before they break down. So just because I showed that your C alpha equals C alpha inverse for 2 points, should that be convincing? No, especially if C alpha's job is to switch these 2 points, right? Here's a map that flips those 2 points. Hey, what a surprise. If you apply it twice, you get back to where you started. How many people think that C alpha does equal C alpha inverse? 1 person. How many people think it does not equal? And that this was just done to deliberately mislead you? All right, so at least a few people were brave enough to vote. But when you look at this, you want to gather some data. What could you do next? Try some other points. How many points do you want to try? We don't have that much time left. How many points do you want to try? 1. Okay, it turns out it worked. Oh, I'm sorry. What point did you want to try? I should ask that first before I say it. Yes, that worked. Oh, wait, z equals 1 is not absolute value less than 1.
Oh, right.
Strictly less than 1. That worked. 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 Yes, worked. Yes. So any point you try, it's going to work. So now we begin to think maybe there's something to this. Maybe there really is an inverse relationship between the 2. And so we want to try to figure out, is C alpha going to be equal to its own inverse? All right, so I've got some algebra on the right-hand side. So C alpha composed with C alpha applied to Z, just plugging in everything in, and then just doing the algebra. And just going through, and at the end of the day, when the dust settles, you return to Z. So this is a function that's its own inverse. And it interchanges 0 and alpha. Now, it would be wonderful if we could show that this function is injective and onto. We should have injectivity right now because it's its own inverse. But let's show that it's onto. So let's take some W. No, I'm sorry. What we're going to do is the following. We're going to take Z to be e to the I theta. Okay? So we're going to take something on the unit circle. Is this function well defined on the unit circle? Well, alpha is less than 1 in absolute value. So if Z is e to the I theta, the denominator is going to be 1 minus something less than 1 in absolute value. I don't have to worry about the denominator vanishing. It's not going to have any issues until the absolute value of z is of size 1 over the absolute value of alpha, which would be greater than 1 because alpha is inside the disk. So I know this is going to be well defined. So I plug in z equals e to the I theta. Okay, so we're using z equals e to the I theta. And so we get alpha minus e to the I theta. And then I'm just going to write z, I'm going to just pull out a e to the minus I theta. And so if I bring this in, you can see e to the I theta times e to the minus I theta is just 1. And then e to the I theta times alpha bar, that's just going to be alpha bar times z. So I'm just pulling this out. And then to make the algebra nice, I'm going to let w be alpha minus e to the I theta. The numerator is just w. I think there's actually a typo here. I think it's off by minus sign. So does everyone agree that the numerator is just w by definition? The denominator is e to the I theta. And what is e to the minus I theta minus alpha bar? This is going to be minus w bar. So I think this was missing a minus sign. So put in times a -1 over there. Okay. Now that we have this, what can you say about the absolute value of c at e to the I theta? This is going to be the absolute value of w over e to the I theta negative w bar. Well, what's the absolute value of w divided by the absolute value of w bar? 1. And the absolute value of e to the I theta is 1. What theorem should I use now? The baby's crying, quickly. Don't you want to comfort the baby? Rouché's not a bad guess. Not Rouché. Maximum modulus, right? We have our function. It's taking on a value of 1 in the interior. What must be true in the on the boundary, right? Could the function be as large as 1 inside? Could it be larger than 1 inside? So by maximum modulus, we know that the absolute value, well, I'll say C alpha of Z is inside the unit disk if the absolute value of Z is less than 1, as cannot attain max interiorly. Because the denominator is not 0, so I can differentiate. So it's extremely important that we stay away from your places where the denominator vanishes. And so as long as alpha is inside the unit disk, 1 minus alpha bar z can never vanish. So we know that the function has to map the unit disk into the unit disk. Do we know that it's onto? Can you find, if I give you, so proof that it's onto. Given, so then you're lucky. Given W and D, right? Consider Z equals C alpha of W. Then what would C alpha of Z be? That'd be C alpha of W, which is just what? W. So it's onto. So we can show that the function is onto. What's nice is essentially a constructive proof that it's onto. One way that I can prove it's onto is I can give you, here is the specific point that's sent to W. Hard to dispute that. And then you can show that you can't have two Z's that are mapped to the same thing. So we've now shown that C is a automorphism from the unit disk to the unit disk. Automorphism just means the outcome and the incoming spaces are the same. And the key idea was the maximum modulus principle. We looked at what the function was doing on the boundary, and we used that to deduce what was going on the inside. So we're going to use the maximum modulus principle up the wazoo on Friday. We're going to keep using it to just deduce more and more properties of these maps. Okay, so this is a good place to stop.